Stoichiometry is such a powerful tool in chemistry, and there's a lot of different ways that we can utilize stoichiometry to find interesting and useful quantities. And one of the important ones that we can get from that is percent yield. Especially as experimental scientists, when we're in a lab, percent yield is really important because it gives us information about kind of how well we did. It's really a measure of how efficient our reaction was, because the percent yield is how much you actually got. Yield is your product, right? How much you actually produced compared to your theoretical yield, which is how much you could have produced in a perfect world. So this actual yield would be something that's either measured, so you yourself produced that much, or this is a given quantity. You were actually given a certain amount. And then the theoretical yield is something that we can calculate. And this is going to be based on stoichiometry. In a perfect world, how much could you produce, right? If you started with X amount of something, then how much would you be able to produce in a perfect world? And then compare it to how much you did actually produce. When we take this ratio and multiply by 100, that gives us a percentage, and that kind of gives you a sense of how well we did. How much did we actually produce? And that's important. And actually, the percent yield is something that for different reactions, you can have different percentages that you would expect. So if you get more or less than that, then there might be a problem with your experimental procedure, or maybe you could tweak the way that you do things. There's a lot of different applications. So let's look at a problem that looks like this. So if I react 6.90 grams of CH4, CH4 is methane, in this following reaction, and 17 grams of carbon dioxide form, what is the percent yield? So this is what is called a combustion reaction. We have a hydrocarbon here reacting with oxygen, and it produces carbon dioxide and water. So this is the combustion of methane. So it gives me information about methane. So if we're thinking about stoichiometry, our first step is to identify our thing 1 and thing 2. So thing 1 in this case is methane, because that's what I'm given information about. And it says that 17 grams of carbon dioxide form. So this 17 grams of carbon dioxide is going to be my actual yield. That's what I actually made. So it told me that. And so since I'm looking for the actual yield of this, or I was given the actual yield of this, I need to figure out the theoretical yield of this. So that means carbon dioxide is my thing too. That's the what am I asked the question about, right? What am I given information about? What am I asked the question about? Now I can disregard everything else in this balanced chemical process because I'm just focused on these two and the molar ratio between them, which in this case is a 1-to-1 ratio. 1 methane for every 1 carbon dioxide, which is good. Okay, so now that I have that figured out, now that I've focused on my thing 1 and thing 2, now I can set up my stoichiometry. So I can set it up starting with the thing that I'm given, so my mass of my thing 1. There's my grams of methane. Now I need to go from grams of methane to moles of methane. Grams to moles. Then I'm going to go from moles of thing 1 to moles of thing 2. Moles to moles, and it's asking for a comparison with a mass here. So I need to have mass at the end of this, so I need to go from moles to grams. Okay, grams to moles, moles to moles, moles to grams. That's our stoichiometry setup. So now I can plug in my numbers. My first one here is the molar mass of methane. So I go to the periodic table, and I find that for every 1 mole of methane, it's the mass of carbon and 4 hydrogens, which is 16.04 grams. Now this part, my moles to moles, my molar ratio comes from the balanced chemical equation. So this is a 1-to-1 ratio. For every 1 mole of methane, I produce 1 mole of carbon dioxide. And now I'm going from moles of CO2 to grams of CO2. So I find this again on the periodic table. And if I take the mass of 1 carbon and 2 oxygens, then I end up with 44.01 grams. Okay, now, if I kind of do some back of the envelope calculations here, so it's essentially 7 times my 44 divided by 16. So I'm expecting that my number here is going to be larger than this number that I had to begin with, right? And how many sig figs are we going to have? It looks like we're limited to the 3 that we started off with. So we'll end up with a number that looks like this, 18.93198 grams. And we said we wanted to round it to 3 significant figures. So that's 1, 2, 3. I'm looking to that 3 to round, which we're going to round down. So that would give us 18.9 grams of carbon dioxide. Okay, so what did I just solve for? Well, I was given the actual yield. It asked me for percent yield, so I needed that theoretical. What I actually just solved for then is my theoretical yield. In a perfect world, if I had 6.90 grams, I should be able to produce, under the exact perfect conditions, 18.9 grams of carbon dioxide. Okay, so now I need to do my percent yield, because that's what it's asking for, is what is the percent yield of this whole process. So I'm going to say that my percent yield is equal to the actual, which is given, 17.0 grams, over the theoretical, which I calculated as 18.9 grams, and I'm going to multiply that ratio by 100%. And when I do that, I end up with 89.9%. That's my percent yield, which means that of the 100% possible carbon dioxide that I produced 89.9% of it, which is actually pretty good. That's a pretty high percent yield. There's a lot of error that goes into real experimental conditions because not all labs have perfect conditions all the time, so this kind of percent yield is pretty good. But it kind of depends on the reaction, depends on what you're producing, depends on where you're producing it, etc. Okay, so this is just one cool application of stoichiometry, percent yield. We'll talk about others in other videos, and if you have any questions, as always, don't hesitate to reach out.